A vector addition diagram is a useful tool when analyzing force problems. It's something that we can use in addition to a free body diagram, and it sometimes helps in being able to tell whether a free body diagram is balanced or unbalanced. Before we can understand exactly what a vector addition diagram is, we first must define a vector. A vector is a quantity that has a magnitude and direction. We've already seen some examples of vectors. Things like displacement, velocity, acceleration, and force are all vector quantities in physics. When we say magnitude, we really just mean that it has a number associated with that quantity. And then, of course, direction. And we can quantify direction by using words like left, right, up, down, or north, south, east, west. And sometimes we also use positive and negative signs for direction. Vectors are represented by arrows. So any time in physics where we've drawn arrows in our diagrams, really we're drawing vectors. Arrows have a specific length corresponding with the magnitude of our vector, and they also point in a specific direction. In vector addition diagrams, or VADs for short, vectors are placed in the tail, as opposed to all of the tails being on the dot as they are in free body diagrams. And as I've already mentioned, vector addition diagrams can help to show whether a free body diagram is balanced or unbalanced. Let's take a look at some examples. Here's a free body diagram for an object that is simply sitting on a table. It has a normal force from the table pointed upward and the gravitational force from the earth pointed downward. In our vector addition diagram, we're going to take these two arrows and place them tip to tail. So if our first arrow is the upward arrow, the normal force from the table, and then our tip of our second arrow will start here, and I'll use a different color just so we can see the difference in the two arrows, and would go downward. Now we can tell from the congruency marks that these two arrows are the same length, and in our vector addition diagram, when they're right on top of each other, we can also see that they're the same length. Now in vector addition diagrams, we also typically label our arrows. And so I would label this normal force with the Fn, as we see in our diagram, and I would label this gravitational force with the Fg. Technically, we should also put the agent in parentheses following that symbol. And so I have my normal force from the table and the gravitational force from the earth. This is a pretty simple free body diagram, and thus a pretty simple vector addition diagram. So let's look at ones that are maybe a little more complicated. This one's very similar, except you'll notice that they no longer have congruency marks. So as I'm drawing this vector addition diagram, I have my upward arrow for the normal force from the ground, and then my downward arrow for the gravitational force. As opposed to the last time that we drew this vector addition diagram, you'll notice that this time, the tip of my gravitational force arrow does not end up at the tail of the normal force arrow. This shows that this diagram is unbalanced. In other words, that when I add these two together, or I put them tip to tail, they do not match up. Let's look at some examples where I have arrows that aren't just up or down. Actually, we're going to do one more example, and this one's going to end up being balanced. This is really similar to a diagram that we had in class. And so I have my upward arrow that shows the normal force from the ground. And then I have two downward arrows this time. One of those downward arrows is the normal force from your hand, and then the other downward arrow is the gravitational force from Earth. And you notice that I ended up in drawing that arrow where I began in drawing my normal force from the ground. That shows that this free body diagram was balanced. Okay, let's see some more examples now. Here's one where I have some arrows pointed up and down and some pointed to the right and left. The order in which you draw these vectors as you're drawing them tip to tail does not matter one bit. I know that my up and down arrows are the same length and my left and right arrows are the same length. I end up getting this kind of closed object. Basically, I ended up right here, matching up with where I started right here. You'll always end where you start if you have a balanced free body diagram. Again, I should label each of these forces with the name of the force and the object that's exerting the force. But for the sake of time, I'm just going to label it with the symbol right now, and you could fill in the object exerting the force or the agent on your own. Here's another example. This time we have a vector that's at an angle. Again, the order in which you draw these vectors doesn't matter at all. I typically end up kind of just going around the free body diagram. So I can get a diagram that looks like this, or maybe if I started with something different, just to show you what that would look like. So let's say that I started with my frictional force and then went downward for the gravitational force, and then at the angle for the tension, and then at the upward force for the normal force there. So I have two vector addition diagrams here that look different, but they're depicting the exact same free body diagram, where this is the gravitational force. The short vector to the left is the frictional force. This is the normal force from my ground acting upward, and this is the force of tension. Now this would be an example of an unbalanced free body diagram, because you'll notice this time that the end of my arrow, my last arrow that I drew, the tip of it, did not match up with where I began drawing, the tail of my first arrow. And that's the case in both of these diagrams. There's kind of this gap there. That's one way of showing that this is an unbalanced diagram. Now we'll talk a bit more later on as we study these diagrams more about how I knew that my gravitational force arrow had to be longer than my normal force arrow. So if you're not quite sure that's the case yet, don't worry, we'll spend more time talking about that. One last example of these diagrams. This is one, once again, similar to what we saw in class, where I have three arrows, and we learned in class and discussed in class that this should be a balanced free body diagram. So let's see what the vector addition diagram looks like. I have my downward arrow here. I have an upward arrow there, and then an upward arrow here. Now you can see that again, I ended where I began. I have this nice closed shape where I don't have any ends of vectors or tips of vectors that don't match up with another tip or end. And so that's a good way of showing that my free body diagram was indeed balanced. We'll spend some time practicing with drawing these vector addition diagrams. Right now, this was just an introduction to show how something like this free body diagram that we see on the screen here can be a balanced free body diagram, even if none of the vectors are the same length as the other vectors.